Okay, so in the last class we started a discussion about the generalized eigenvectors. And what was generalized eigenvectors? Instead of multiplying the vector with a minus lambda I, if a minus lambda I multiply with u is equal to 0, then of course it was eigenvector. But if this not turn out to be non-zero, then you can multiply with higher power of this matrix, and then in such a way that you get 0. Okay, so if you get a smallest such k, then you get a generalized eigenvector, and this smallest such k is called index of this generalized eigenvector. Okay, and then we constructed a from one generalized eigenvector we constructed a set of generalized eigenvectors of the lower index and are also an eigenvector. So if you look at this recursive relation, this was a this was eigenvector and these were generalized eigenvectors. Okay, so this was generalized eigenvector of order 1 and so on and so forth. In the end you have to get this is generalized eigenvector of this is generalized eigenvector of order index 2, and this is generalized eigenvector of index k. Okay, so this is the way to from the generalized eigenvector you can go to the eigenvector, and on the way you construct several of them. What we are going to show you now is that these VIs we have constructed in here are basically linearly independent. Okay, so let us write it as a theorem. Suppose VIs are generalized eigenvectors. Okay, eigenvectors of n cross n matrix, then they are linearly independent. Okay, so of course you immediately should realize that if they are corresponding to different generalized eigenvector corresponding to different eigenvalues, then of course they will be linearly independent. What we will consider the case is that if they are generalized eigenvector corresponding to the same eigenvalue. Okay, so proof is fairly simple. Let's look at the proof. We'll consider the case of n is equal to 2, and for simplicity we consider n is equal to 2, so that means A is a 2 cross 2 matrix, and then you will have one eigenvector and one generalized eigenvector. Okay, so all right, so that means you will have u, I take to be u and v, we take to be two generalized eigenvector. Of course one of them will be an eigenvector. So if you take it this way, then obviously one of them will be eigenvector, so you will have some relation like this. Okay, so here note carefully, this will be an eigenvector, this will be a generalized eigenvector of index 2. Okay, now once you have that, we need to show they are linearly independent. So we take two constant C1 and C2 such that C1 of U plus C2 of V is equal to 0, and to show that C1 is equal to C2 equal to 0, this is what we need to show. Okay, so let us consider this relation. Yes, C2V. Okay, this is equal to 0, but U is basically A minus lambda I of V. Okay, So this implies that C1 A minus lambda I of V plus C2 V2 V is equal to 0. Now proof has to be in such a way that you can basically get the complete, you can generalize it for the n case, otherwise you have to modify the proof a little bit. So in keeping that spirit, we are not going to exploit that we are in R2. We are still going to write a proof in such a way that if you have n generalized eigenvector, then you can repeat the proof. So keeping that in mind, let us multiply this with A minus lambda I. Okay, so if you multiply this with A minus lambda I, so you get A minus lambda I square V plus C2 A minus lambda I V is equal to 0. Okay, now clearly this term will be equal to 0. Why? Because n is equal to 2 and lambda is an eigenvalue. So the characteristic polynomial will be of degree of 2, and this is a characteristic degree of polynomial 2 satisfied by lambda. So lambda is a root, so this will vanish. All right. So with that, what you get is C2 A minus lambda I V equal to 0. But not that this is equal to U. So this implies that C2 of U is equal to 0. But U is an eigenvector, right? So it cannot be 0. So that means this implies that C2 is 0. Okay. And when C2 is 0, you can either plug this thing here and then you get C1 to be 0, or you can do something else also. There is absolutely no issue. So this implies C1 is equal to 0. Okay. So that means if you have two generalized eigenvector of different index, of course, if there will be two different eigenvectors, generalized eigenvector corresponding to the same eigenvalue, then they will be linearly independent, and that is because they have a different index. So they will have this kind of relation where one of them will be 0, one of them will be not be 0. All right. So now, with that in mind, let us go ahead and try to prove the existence of such a generalized eigenvector. Okay, what is the, so far we are assuming there is a generalized eigenvector and then trying to do it. What we are going to do is that now we are going to prove that there indeed exists eigenvector and of course the generalized eigenvector. All right. So let us write it as a theorem. Now suppose again we will consider the case, simple case, so that the analysis is easy. N is equal to 2. Okay, so we are in 2 dimension and lambda is repeated eigenvalue. Of multiplicity 2, of course. But geometric multiplicity is 1. Repeated eigenvalue of, let's say, A. Okay. Then in this case, then there exist vectors of, okay, let's write generalized eigenvectors of index 1 and 2. All right. So that, okay, so how would we go about it? So you take proof. If you have lambda as an eigenvalue, so this will be a zero matrix. This is the first observation. Okay, by Cayley-Hamilton theorem. Okay, so now this means that kernel of A minus lambda I square is equal to whole R, right? Or the dimension of this kernel is 2. But we know that dimension of kernel of A minus lambda I, which is nothing but the set of the subspace spanned by the eigenvectors, is equal to 1. That's why geometric multiplicity was 1. Okay, so this implies that the kernel of A minus lambda I contains strictly, that means there are vectors outside this kernel which are in kernel of A minus lambda I square. Okay, now we'll take a vector here. Okay, such that Z belongs to kernel of A minus lambda I square, but Z does not belong to kernel of A minus lambda I. That means Z is not eigenvalue, but it's a generalized eigenvector. So Z is not an eigenvector, it's a generalized eigenvector of index 2. Okay, so now because Z is a generalized eigenvector, so okay, let us look at A minus lambda Z. Okay, now this, if you multiply with A minus lambda I, will be equal to A minus lambda I square Z, which is equal to 0. So this implies that A minus lambda I Z is an eigenvector. Okay, so this implies that it will be in the kernel of course, this is what it means, that this vector is in kernel of A minus lambda I. So it's an eigenvector. Now if our eigenvector is U, that means, so if U is eigenvector, note that because lambda is an eigenvalue, there will always exist one eigenvector. Otherwise, you cannot say lambda is an eigenvalue. Okay, this is by the definition, eigenvector corresponding to lambda. Okay, so this means that A minus lambda I Z will be equal to alpha U for some alpha. Okay, so this means V, which you can take to be Z or Z by alpha, is the required generalized eigenvector with index 2. Why? Because note that A minus lambda I of V is U. So what we did is we compensated for this alpha what appeared here. Okay, so this proves the existence of U, which come from the definition that lambda is an eigenvalue, and V from the existence of such a Z. And this came out because of this strict inequality, that the kernel of A minus lambda I is contained strictly in kernel of A minus lambda I square. Okay, so with this we can be sure that it is possible that we don't have all the eigenvectors, but we can always get replace missing eigenvectors with the generalized eigenvectors, and they will be linearly independent, as I just proved in the previous theorem. All right, any questions so far? Any questions so far?
Sir, can you explain that U is equal to Z by alpha part?
Okay, just 1 second. U equal to Z alpha y. Yeah,
Z by alpha is a generalized
alpha.
eigenvector. How is it a generalized?
Oh, so this, if you put Z by alpha here, this is my definition of V. If you put Z by alpha here, you get alpha of alpha, 1 upon alpha of U, alpha get cancelled.
Okay, okay.
If you want, I can write it. This is equal to A minus lambda I Z by alpha, which is equal to 1 upon alpha of alpha U, which is U. It's only thing I wanted equality to be U. Although it doesn't matter if you, yes.
So how you write this step A minus lambda I into Z vector is equal to alpha U like this?
Okay. So note that here we are in the case n equal to 2, right? So that means there is always an eigenvector, but one eigenvector is missing. So we are going to replace it with the generalized eigenvector. So effectively we are trying to prove that generalized eigenvector exists. So note that, look at this vector. When you multiply this vector with A minus lambda, you get a 0. That means this vector is an eigenvector. That means it is in kernel of A minus lambda. A minus lambda. That means it will be spanned by U, right? Because kernel of A minus lambda is spanned by U. Is this fine?
Yes, sir.
So look at the what is spanned by U, and that would be the situation. All right. Okay.
So for
So
n is equal
now,
to 2, it is clear, but for greater n, how will we do it? Because then it will be spanned by other vectors.
yes, that is true. That is true. That it will be spanned by other vector. You can, I think, in that case. Okay, so if you have in that case, let's say you have two vectors and one missing, right? This is what you want to say, right?
Yes, sir.
Yeah. So in that case, let me try to do it here. So that means you will have n minus lambda I cube Z is equal to 0, and you will have two eigenvectors. Okay, so you will have two eigenvector. Let's say call them u1 and u2, right? All right. So that means kernel of A minus lambda I and okay, so this will be A minus lambda I square Z. So in that case it will be square here, right? Because that will be the eigenvector. Okay, so you'll get alpha plus beta. Okay, just 1 second. I'm trying to yeah. Just 1 second. So okay, yeah, you're right. Let me give the proper argument for that case. that let us assume that lambda is 3 times repeated. You have 2 eigenvectors, but one is missing, right? So that means let us take a, I think in that case you can pick any of them, but let's see. Let us consider one eigenvector v which is equal to u1. Okay, my claim will be that this is the generalized eigenvector. So why it will be generalized eigenvectors? So this will be basically a minus lambda I square. When you apply on this thing v, this will be a minus lambda I u1, this will be 0, and of course a minus lambda I v1 is not equal to 0. So clearly this is a v is a generalized eigenvector of index 2. Okay, v is a generalized eigenvector of index 2. Of index 2. Okay, now the question is that whether such a v exists or not. Agree? So now let us see. So the kernel of a minus lambda I square is bigger. How would we argue about it? So I think you can still argue like this. So if your characteristic, because lambda is 3 times repeated, so cube equal to 0, this will make everything 0, and if you have square v, now v is also 0, so I don't care about the other part. I think in that case you can take any of the one of them. If you're two now, you can take any one of them, and then the only question left is that can I find such a v? So you can take either u or u1 or u2. It's your choice. You can take any of them. Okay. The question is that whether what is the guarantee that such a v exists? And to guarantee that, we need to show something similar. Where is this? We need to show something similar here. Where is that containing this one? So this, if you take v to be something like this, so okay, so so if you take kernel of a minus lambda I, the dimension of this is 2. Okay, if you look at kernel of a minus lambda I square, clearly it's bigger than kernel of a minus lambda I, but the important point is that I need to find a vector here where such that this does not belong to this one but belongs to this one. That is the only part left. Okay, so if I prove that the a minus lambda I square is equal to 0, then I am done. Okay, if I prove that the dimension of a minus lambda I kernel of this, if I prove that dimension of kernel of a minus lambda I square is equal to 3, then I'm done. Okay, so ideally I need to prove that not only this is 0, I need to prove that a minus lambda I square is equal to 0. Okay. Okay, how would we prove that? I think we have to use some Cayley-Hamilton kind of argument, and that if you look at the characteristic polynomial, then you get so because lambda is repeated 3 times, so something like this is 0. Okay, and because yeah, I had to see that. It's probably not that straightforward. But one has to prove this argument something like this. Okay.
So basically, if we prove that a minus lambda is equal to square is equal to 0, then we can say since
Then
dimension will be 3.
Then we can say that, yes. Yeah. It's probably yeah. So yeah, that is the point. Basically, you have to show that there is a some vector here which doesn't belong to here. I can also take 3 here. Actually, if I take 3, so clearly if I take 3, that is the case, right? Because the dimension of the multiplicity is 2 here, geometric multiplicity, and geometric here is completely 3 space. Yes?
Yes, sir.
So let us take that. So you take V or Z, and let us try that angle. Maybe Z is such that A minus lambda I is this belongs to kernel of cube, but the Z does not belong to kernel of A minus lambda. Okay. Then you can argue that Z is the so that means A minus lambda I Z square at least will be an eigenvector. So this will be alpha of u1 plus beta of u2. Okay. So now I need to show that I need to show that Z is the okay. So so if I show one of them is 0, then it's fine, but I don't want to show that. That would not be the ideal. So there exists such a Z, that is very clear. For such a Z exists. The question is that I want index of Z to be 2, not 3.
So alpha u1 plus beta u2 itself is an eigenvector, right?
Yes, that is fine. That is not an issue. My
we
problem
can
is
take
here I have a 2.
No, we can show that Z is indexed to with respect to that eigenvector alpha u1 plus beta.
I want index to be 1, not 2. Of course, 2 is clear.
Yeah, I mean, I don't think we can find an index 1. It's not necessary.
I mean, so if you find index 2, you can always find index 1.
Yeah, right.
Okay, so that is not an issue. So from that, if you get that this is index 2, then you can just multiply this by A minus lambda Z and that let's call it Z1. This will be index 1. So index 2. I need index 2, not 3. Okay, so this is index 3, not 2. Okay, this is index 3 because 3 is 0. So then you can get an index 2 like this. Yeah, something like that is probably needed. Okay, so let us assume that this is the case, and we are going to argue that A minus lambda Z is the desired. Yeah, something is missing. Let me work out. Maybe in the next class I'll explain something. Okay.
Okay, sir. Thank you.
Let's go ahead. We are wasting bit time. Not wasting, but it's going on in discussion. Okay. So let me continue for the timing, and I will try to think about it and write it in a proper. All right. Anyway, very nice question. So let us go forward. So that means we have proved, and assuming that we overcome this issue, is that if that we can find eigenvector, generalized eigenvectors. Okay. Okay. All right. So I can probably argue in some way, but okay, let me not go back. So now with this we'll define at least for n equal to 2 case, our 2 cross 2 Jordan block. Jordan block associated with with an eigenvalue lambda is a 2 cross 2 matrix of the form J equal to lambda 1 0 lambda. Okay. All right. So now all right. So just to clarify this argument which you have asked, in the end, I don't care if I have additional eigenvector or not. Just to clarify, I can just pick one of them and find the remaining missing generalized eigenvector. So if, for example, multiplicity is 3, algebraic multiplicity is 3, even if the algebraic multiplicity, geometric multiplicity is 2, I pick one of the eigenvector and find the remaining 2 missing eigenvector, find the 2 missing generalized eigenvector. So I don't need to care about the other eigenvector to just say that it's not important. I can just take one and find the other two. Okay. So this can be carried out. This discussion can be carried out without considering these two cases, these two things. Just pick one and just carry forward. Okay, you can do that. Okay, so let us go, get back to the case, and then why I'm doing it. Now what we'll do is the following. So why these kind of things are important, and this has nothing to do with the 2 cross 2. You can write it n cross n version of it. So similarly, I'll just write similarly n cross n block, Jordan block will be of the form J lambda 1. So on diagonal you will have lambda, and on the immediately after the diagonal entry you will have 1. So similarly lambda 1 and 0 0 0 0. In the end you will have lambda. Okay, other entries are 0. Okay, so this is very close to the diagonal matrix. Only thing is that you have only one entry just after the diagonal entry is 1. Okay, and it will what we will aim to show now in this discussion is that any matrix A with the real eigenvalue will be similar to something of this form. Not exactly this form, but it can have some other blocks also. So some which will contain basically with the blocks of this kind. So let me try to say again. So let us do that for 2 cross 2 case, and then it will be clear to you what I'm trying to say. Okay. So let us write theorem. Suppose n equal to 2. Okay, and lambda is repeated eigenvalue. Okay, with geometric multiplicity 1. Okay, so of course algebraic multiplicity will be 2. Okay, so in that case clearly you will have one eigenvector. So we'll have eigenvector. Let us denote that eigenvector with u, and you'll have one generalized eigenvector. Okay, which will be of order 2. Okay, of course this will be, because eigenvectors, it will be order 1. Huh? So that means a minus lambda is 0. In this second case, a minus lambda is square applied on this v will be 0. Now if that is the case, then the matrix A, and so who has this property, huh? A eigenvalue with geometric eigenvalue, repeated eigenvalue of A. Okay, so everything is related to A. Then A can be written as A is equal to P J P inverse, where this matrix P is an invertible matrix containing vector u and v. Okay, the first vector is the eigenvector, the second one is the generalized eigenvector of index 2, and if you have more than one, then you will have generalized index vector of 3 and 4 and 5, fifth order, and so on and so forth. Huh? So you can continue that. And J is a Jordan block of order 2 corresponding to lambda. Now you can see that what I am doing. So if you happen to have two eigenvectors, then the matrix will be diagonalizable, and you can find such a P and such a J such that this happens. But here, because the matrix A is not diagonalizable, in that case you can make A almost diagonalizable, but it will have one more extra entry here, this one. Okay, of course when A is diagonalizable you can still do this, but it won't be, it will be useless in some way. Okay, but if A is not diagonalizable, then also you can do it. That is the important part. If A is diagonalizable, probably you don't want to do that, you want to make this to be diagonal. But even if A is not diagonalizable, you can always do that, provided it has real eigenvalues. This is what we are going to prove. Okay, so proof. Okay, so note that A minus lambda I u is equal to 0 and A minus lambda I v is equal to u. Okay, these are the two equivalent. So in case of, again, if you're two eigenvectors and one missing, you can take any of the one eigenvector and find the other two generalized eigenvector. We start with one and find the other two. So even in case of 3 cross 3, it will be fine. You can always do that. This is what I'm trying to tell you. Okay, and after I finish this 2 cross 2 case, I will discuss this 3 cross 3 case once. Okay, so all right, so then of course that will also finish the discussion what I was missing here, right? Because then I can always say that there are other, instead of having one missing generalized eigenvector, we'll have two eigenvectors, even if you're only one missing eigenvectors. Okay, all right, so let us go ahead. And then in this case we are almost done. We define the matrix P.
Sir?
Yes.
Sir, like here, shouldn't it be like alpha u? How do we know it's exactly u?
We make it by scaling it. Now this is what we scaled.
Okay.
We can always scale it. Where did we scale? This is the scaling. No? You can always scale it. That's not a big deal.
Yeah. Okay, sir. Got it.
If U is an eigenvector, alpha U is also an eigenvector. So that is not an issue. Okay. So, so P of course will be equal to U1, U2 and V1, V2. Okay, this is what I mean by here. And maybe I should write it, do it a better job. If you can want to write it this way, you can write it this way. Okay. Then J is lambda 1, 0, lambda. I'm not going to do anything fancy. I'm just going to directly compute because these are simple cases. Okay. What I want to show that A of is equal to P J P inverse. But instead what I will show is that P of A, A of P is equal to Pj. This is what I'm going to show. Of course, P is invertible matrix because these are linearly independent, so that will automatically follow. So let us do that. A of P is nothing but A of U, A of V. Okay. Now A of U is lambda of U from here. A of V is U plus lambda of V. So let's write lambda of V plus U. This is important. You pay attention onto this. So I can write this thing to be equal to lambda of U. So and this will be lambda of V plus U. To be more precise, this will be lambda U1, lambda U2, and this will be lambda V1 plus U1, lambda V2 plus U2. Okay, so this is the calculation for this side. Calculation for this side is trivial because this is a very simple matrix. So Pj and J is nothing but lambda 1, 0, lambda. So Pj will be equal to this multiply with this. So this is 0. So only in the first case you will get lambda U1, lambda U2. When you multiply this with this, you see this is 1. So you get U1 here. So you get lambda V1 plus U1 and lambda V2 plus U2. And clearly this matrix is same as this matrix. Okay. Now let us look at case n is equal to 3. Okay. I assume I have algebraic multiplicity is 3, but geometric multiplicity is less than 3, strictly less than 3. Okay. probably won't care whether this is 2 or whatever it is. Okay, so in that case, what I will get is, so I will have 3 eigenvectors, sorry, 1 eigenvectors and 2 generalized eigenvectors. So assume that u1 is the eigenvector, u2 is generalized eigenvector of order 2, sorry, order 3. So u2 will be a minus lambda I u2 is equal to u1, and similarly u3 will be something like this. Okay, so this will have index 3, this will have index 2, or other way around. So this will have index 2, this will have index 3. Okay, now P matrix in this case will be u1, u2, u3. J will be lambda, lambda 1, 0, 0, lambda 1, 0, 0, lambda. Okay, and A is your matrix. So what you need to check is that AP is equal to PJ. You have to check. They will be equal. Okay, the calculation is same as I told you, just you have to use these 3 equalities, and in addition, of course, you should use that a minus lambda u is equal to 0, sorry, u1. Okay, so if you use that, you'll get this block. So here I'm not caring about any other eigenvector, I just stick with one and then I get the other 2. Okay, and this to a certain extent answered the questions what we are trying to ask. What if you have 2 eigenvectors but 1 missing? I don't care about 2, I just stick with 1. Okay, I start with 1 and 1 is guaranteed because lambda is an eigenvalue. Okay, and then I can repeat the process. All right, so with that I stop here, and basically what you should take from today's discussion is that if you have matrix A with the same eigenvalue, and of course if it has different eigenvalues, I'll tell you how to do that in the next class, but if the same eigenvalues and some vectors are missing, then you can write them in the Jordan form, Jordan block form, and this is called Jordan. So this is Jordan block of order 3. Okay, that was Jordan block of order 2. In the next class, what I will do is that I will take a general matrix A with the real eigenvalues and write it in the using several of these blocks, because for each eigenvalues I will either have a diagonal block or I will have a Jordan block, and the size of Jordan block will be the algebraic multiplicity of that eigenvalue. Okay, so for example, if A has 2 eigenvalues, okay, let's say lambda 1 and lambda 2, and it has, this one has multiplicity 2 and this has algebraic multiplicity 3. Now if geometric multiplicity is 2 here and here it's less than 3, then the block or this matrix J, big matrix J, will look like this. This will be lambda 1, 0, 0. Okay, because you already have 2 eigenvectors, so this will look like this. Okay, now if something is missing, I want k, then I will just write lambda to 1, lambda to 1, lambda 2, and all the other entries are 0. Okay, and the matrix P will be containing these two eigenvectors for the first part. So let's call them u1, u2. These are the eigenvalues corresponding to lambda 1. And then remaining one will be, the first one will be the eigenvector corresponding to this case. And then the two generalized eigenvector. Okay. So in general, in principle, for any matrix P, you can write it as using Jordan blocks. So this is one Jordan block, this is second Jordan block. Of course, if in this case geometric multiplicity is 1, then you will have 1 here. And here you will have here you will have generalized eigenvector. So idea is that if you are missing eigenvector, use generalized vector, then you won't get a diagonal matrix, but you will get a Jordan canonical form of the matrix. Okay, this is called Jordan form of the matrix. So for any matrix A with a real eigenvalue, you can do that, independent of whether it's diagonalizable or not. If it's diagonalizable, then note that J will be exactly the diagonal matrix. If it's not diagonalizable, you will get the just one non-zero, one of diagonal entry will be non-zero. Okay. So with this, I stop the recording and then I will take your question.